Today we're going to talk about rates of change and tangent lines. Um, and I'm always a little confused at this point in the year because I'm teaching A, B, and BC. So I'm like, wait a minute, which have I talked about that in this class? Did we talk about the average rate of change?
I think we did it like one of the first lessons.
Okay, so average rate of change is just how much something has changed divided by whatever interval it is. Frequently, that's a time interval. It doesn't have to be time. You can do, you know, the, I don't know, the number of apples picked per worker, right? Right. You could do the average rate of change of the number of apples picked, right? So it's the amount of change divided by the length of the interval. Graphically, it looks like this. If you have the graph of y equals f of x from x equals a to x equals b, then the average rate of change is the slope of the secant line. So this slope, oh, hang on. Sorry, didn't realize it wasn't on already. So the slope of this line is equal to the average rate of change. Want you to notice a couple of things. Because I drew this as a continuous function, and this is something we'll do later on, you don't need to think about it very much right now, but notice if I go right about there, there's another place where this is the rate of change at this point is equal to the rate of change on average. And then there's another point here. It makes sense that if you have an average rate of change over some interval that's continuous, that the instantaneous rate of change has to be equal to that at some time. Let me give you a quick example. If you average 60 miles an hour on a trip someplace, well, at least once you had to be going 60 miles an hour, right? We'll actually talk about that a little bit later on. That's called the mean value theorem. But that's not for today, so we won't worry about that. So, here we have an example that's not velocity. Sometimes it's hard to come up with ones that aren't. Velocity and acceleration are just great examples for a lot of things. But after introducing an organic pesticide to a fruit fly colony, boy, I could use some of that in here, the number of flies dropped from 340 on day 23 to 150 on day 45. Find the average rate of change. All right, so the average rate of change will be the change in the quantity. So it's 150 minus 340. It's where it ended minus where it started, over where it ended minus where it started in terms of the time interval, 45 minus 23. So this is what, negative 190 over 22? If I've done the arithmetic correctly. Always correct my arithmetic. I'm frequently thinking about the next thing we're going to talk about, and so that's my excuse for being bad at it. The truth is I just don't always pay enough attention. So since that's a pretty horrible number, I'm going to give a decimal approximation. It's approximately negative 8.6 fruit flies per day. And it's negative because the number of fruit flies is decreasing. That totally makes sense to us at an intuitive level. All right, page 2. So a tangent to a curve, there's a lot of uses for this. direction of motion is one of them. If you think about, if you're driving on a curved road and your car is currently right here, your direction of motion, if you just let go of the steering wheel, right, your direction of motion is tangent to the road. Okay, that's why when you turn, you feel a pull that direction. Mr. Mosley can probably say it in all the right words, but that's what you're feeling. It's because this is my current direction of motion and I'm changing that. That's why I feel some sort of a pull. But there's a lot of other ones. Optics and satellite receivers. Optics and satellite receivers actually work in kind of the same way. You know, when you have a satellite receiver, part of what you're doing is, you know, this is coming in at this, and you have your tangent, and it comes off to where this angle and this angle are the same. It's the same thing if you're playing pool. It's I don't know if they still say it this way. The angle of incidence is the angle of something else. No? Okay. The angle that it comes in on, it comes out at the same angle. Right? That idea. And how do you do the angle to a, you know, you're like, well, it's a curved surface. How am I going to do that? You use the tangent line for that. Okay? So it gets used in all kinds of places. The idea of an instantaneous rate of change has way more uses, but it all starts with this. So I'm going to show you what's called Fermat's method for defining tangents. So here are the steps. First step, find the slope of the secant line through a point P and a nearby point Q. Step 2, find the limiting value of the secant slope, if it exists, as Q approaches P along the curve, that is, as the distance between P and Q goes to 0. So as those 2 points get closer and closer to each other. So here's what's going on. Let's say we've got a curve that looks like this, and we're interested in the tangent line at this point P. What you do is write an expression for the slope of that secant line. And then you start moving Q to the left along the curve, and as it gets closer and closer and closer, you get better and better approximations of something that would be tangent to the curve. And that's the idea. As the distance between these 2 points goes to 0, you actually get something that is tangent to the curve. And you're like, now, what does that mean? Well, it means it's only going to go through the graph of the function in this one place in this area. It also means if you were to have this on your calculator, if you were to zoom in on this little piece right here, I think I may have showed you guys this, that the graph of the function and the graph of the tangent line become completely indistinguishable from one another. It looks like exactly the same thing. Okay? So then the slope of the curve is this limiting value, and the tangent to the curve is the line through P with this slope. So let's do an example of that. Find the slope of y is equal to x squared at the point 2, 4. Write an equation for the tangent line at this point. Okay, so our p-value, if you will, from the general instructions is 2. So our P is at 2, 4. And what we're going to do is our Q value, and there's nothing magic about P and Q, and after a little while you won't even write those letters at all. But our other point, we want it to be nearby. So what I'm going to do is say that it's going to be 2 plus h will be its x coordinate. And you may be going, why would you use h? Well, I'm moving horizontally, right? From 2, I'm doing x values, so I'm going from 2 to 2 plus something. And then the y value would be 2 plus h quantity squared, because that's the function. So the slope for PQ, or the slope of the secant, is going to be equal to the change in y over the change in x. You can do it in any order, but it's generally easier if you do Q then P. So that'll be 2 plus h quantity squared minus 4 over 2 plus h minus 2. So then to find the slope of the tangent, we want to take that and find the limiting value as Q gets close to P. As Q moves closer and closer to P, what's going to happen to H? It's going to get down to close to 0. So we're going to take the limit as H goes to 0. Two plus h quantity squared minus 4 over 2 plus h minus 2. If we try to evaluate this limit by direct substitution, we find that it's 0 over 0. That's always going to happen on this. So we've got to algebraically manipulate this so that it's not. So that's going to be the limit as h goes to 0 of squaring the 2 plus h, we have 4 plus 4h plus h squared minus 4 all over h. The h in the denominator makes sense. H is how far apart horizontally, again, that's why it was called h, these 2 points are. Notice that the 4 and the negative 4 add together to make 0, so we'll have the limit as h goes to 0 of 4h plus h squared over h. And then what can we do to that? Because this is still 0 over 0. I haven't done anything to not make it 0 over 0 yet. Yeah. And you're like, wait a minute, I can't divide by 0. We don't care what happens at 0. Since we don't care what happens at 0, we're unconcerned about the fact that you're like, well, wait a minute, you're dividing by something that's going to 0. Yeah, but it's never equal to 0. It's close, but not equal to. So that'll be the limit as h goes to 0 of 4 plus h. And that's 4. So now I've got the slope, I've got a point. We can write the equation in point-slope form. I'm really big on point-slope, partly because when we get further down the line, we're going to actually take the idea of point slope and we're going to expand it to polynomials. Okay? So my tangent line equation and the other thing you'll find, I'm really big on make sure you're labeling everything. It's super helpful for when you're going over homework. It's also on the AP exam. It makes it so much easier for people to know what it is that you're doing. If they have to guess, sometimes they won't. Sometimes they guess wrong. Okay? So the equation is going to be y equals, and for point slope, I do this one. Y equals y1 plus m times x minus x1. Again, the reason I do this in that particular order is because when we get to series in March or April, we're going to expand that. So the y value was 4, plus the slope turned out to be 4, times x minus 2. Your book is never going to leave it in this form. I am always going to leave it in this form. Point slope is sometimes the redheaded stepchild of the Algebra 1 world. But in my opinion, it's way more useful than slope-intercept is. Because sometimes the intercept doesn't mean anything, and sometimes the intercept is a horrible number. Right? So I'll just leave it like this, and you are welcome to as well. When you're checking your answers in the book, you probably need to change it to slope-intercept just so you can check your answer. But I'm always going to leave it in point slope. All right. A normal line to a curve is a line that is perpendicular to the tangent at that point. So this is the equation of the tangent. If they asked you for the equation for the normal, that's just going to be y is equal to 4 minus 1/4 times x minus 2. Goes to the same point, it's just perpendicular to that. Normal lines also have a lot of things that you can use them for. For those of you going on, what are you guys planning on studying? I have no idea.
I don't know exactly yet, but probably something STEM. So.
Okay.
I went to biology.
Biology? Interesting. I don't know what you would use it in for biology. But in engineering and stuff, there's a whole bunch of things where you want the normal line. All right. So let's move on to page 3. So this defines what we just did. In slightly different terms, it's much condensed from Fermat's method. The slope of a curve, y equals f of x at the point a f of a, is the number m, which is the limit as h goes to 0 of f of a plus h minus f of a over a plus h minus a. Notice the denominator is always going to end up being just h. Personally, I think it's a good idea, not a requirement, but a good idea to start with this to remind you I'm finding the slope between 2 points. To remind yourself of Fermat's method. Then I think it's easier to go, okay, I know what's going on. This is always going to be h. So, let's take a look at this. Let f of x be 1 over x. What is this? Find the slope of the curve at x equals a. So when it says that x equals a, we're going to be doing this in general then. Where is the slope equal to negative 1/4? What happens to the slope as x goes to 0? What happens as x goes to infinity? All these questions. So the slope at x equals a equals the limit as h goes to 0 of f of x plus a, or excuse me, f of a plus h, so that'll be 1 over a plus h, minus 1 over a, all over a plus h minus a. Always, always, always on these, when you first substitute in, you get 0 over 0. So there's always got to be something that we're going to do to help us out so that it's no longer 0 over 0. In this particular case, what's going to be helpful to us, in the denominator we're going to change that to just h. But in the numerator, what we're going to do is clear the fractions, because this is what is called, I guess it's no longer fashionable. This is called a complex fraction. It's a fraction within a fraction. Final answers for things are never simplified if they're complex fractions. You should always clear the complex fraction part. How do you do that? You multiply by the common denominator. We're going to multiply this times a plus h times a. And since we're doing that to the numerator, we also have to do that to the denominator. So that I'm multiplying by something that is equal to 1. So that's going to be the limit as h goes to 0. When I multiply 1 over a plus h times a plus h times a, I just get a. Because the a plus h's will cancel. And when I multiply 1 over a times a plus h times a, I just get a plus h. All over, this first factor in the denominator is just going to be h. And in the denominator, I'm never going to expand things, because the denominator is not where the problem is. The problem is in the numerator. I want this in factored form. So a plus h times a. So that'll be the limit as h goes to 0 of, in the numerator I get negative h over h times a plus h times a. And we do just like we did in the last one, divide by h. I can do that because h over h is always 1 except at 0, and I don't care what happens at 0 because this is a limit. Now if I let h go to 0, I've got negative 1 over a times a. I've got negative 1 over a squared. So where does the slope equal negative 1/4? Well, that means negative 1/4 is equal to negative 1 over a squared, which means 4 is equal to a squared. So a is equal to plus or minus 2. That's the answer to the first question. What happens to the slope as x goes to 0? Okay. And when they're saying as x goes to 0, it's the same thing as letting a go to 0. So what is the limit as x goes to 0 of negative 1 over x squared? Well, the numerator is always going to be negative. Denominator is always going to be positive. So if I get a signed answer, it's got to be negative. As the denominator gets really small in a fraction, what happens to the fraction? Really big, right? There's an inverse relationship there. If the denominator is really big, the fraction is really small. If the denominator is really small, the fraction is really large. So this is going to be negative infinity. And just a quick aside, if we look at y equals 1 over x, and we look at a tangent line like at this point, that's a pretty big negative slope, and so is it here. Right? And the closer we get to 0, the closer those branches are to being almost vertical. So the tangent lines become almost vertical. But they have a negative slope all the time. And then what happens as x goes to infinity? So if I take the limit as x goes to infinity of negative 1 over x squared, the numerator is always negative 1. The denominator is really big, so the fraction is, yeah, goes to 0. So this expression, f of a plus h minus f of a over h, is called the difference quotient. You already know how to use it, but that's the term for it. So a quick question, does the curve f of x equals negative 2x for x less than 1, and f of x is equal to x squared minus 3 for x is greater than or equal to 1, have a tangent at x equals 1? And we want to explore that graphically. Now, on your calculator, you can absolutely do piecewise functions. Okay? Let me show you how. You got your calculators? Let's do this. Clear that out. There we go. All right. So what I can do, you have to use some parentheses. We'll do negative 2x. And then I'm going to do divided by, and under the math menu, oh no, sorry, second math, there is a test. What I want is I want x to be less than 1, right? What this will do is if x is less than 1, it returns a 1. So you're dividing by 1. If x is not less than 1, it returns a 0. So you're dividing by 0 and it's undefined. So it won't graph it. So back to my y equals, I'm going to divide this by x. And again, second math is less than, which is number 5, 1. That's the first branch. You can do the branches separately, or you can put a plus sign in between the two and it all becomes one thing. Right? I do them separately most of the time. It doesn't really matter, at least in most cases. So x squared Sorry, I hit a wrong button somewhere. X squared minus 3 in one set of parentheses divided by parentheses x greater than or equal to 1, which is number 4. And I'll do a zoom standard on this to see what it looks like. And you're like, oh, that's really weird. I'm going to zoom in on this. I'll zoom in at 0, 0. Is that a nice smooth curve right there? No. If we were to look at the difference quotient and do the limit as h approaches 0 from the left, we would be using this branch. And if we were doing it as h approaches 0 from the right, we would be doing this branch. And what's going to happen is those two slopes do not agree with one another. Keep looking at the wrong schedule. 10:50. 10:50? Oh, we have lots of time. Okay, let's do this then. So, if I take the limit as h approaches 0 from the left of the left-hand branch, I'm going to be using the negative 2x. So that's going to be negative 2 times x plus h minus negative 2 times x, all over x plus h minus x. So that'll be equal to the limit as h goes to 0 from the left of negative 2x minus 2h plus 2x all over h. The negative 2x drops out, the h's divide out, and this is just negative 2. Which makes sense. This is a linear graph, right? What is its slope? Negative 2. Oh, okay. The slope of the curve is negative 2. Let's look at the other side. The limit as h approaches 0 from the right of, we're going to have x plus h squared minus 3 minus x squared minus 3 all over x plus h minus x will be the limit as h goes to 0 from the right of, we're going to have x squared plus 2xh plus h squared minus 3 minus x squared plus 3. Got to be sure to distribute the negative sign there. All over h. So that's going to be the limit as h goes to 0 from the right. The x squareds will subtract off or add together to be 0. The negative 3 and the positive 3 adds together to be 0. So I'm left with 2xh plus h squared over h. Well, that's going to be equal to the limit as h goes to 0 from the right of 2x plus h when we divide. So that'll be the limit as h goes to 0 from the right of 2x. And my x value is 1, right? So at x equals 1, the slope is equal to 2. The right-hand branch has a different slope than the left-hand branch does. Because of that, we do not have a tangent at x equals 1. So the answer is no. Be sure to answer the question on these. Occasionally on the free response section of the AP exam, a student will go through and do all this lovely work and never actually answer the question. Any questions about that? Okay. I think that was it. Yeah.